Good afternoon, everyone. My name is Mohan Parthasarathy from Thomas Jefferson High School for Science and Technology. And today I'm here to present alongside my mentor, Dr. Parthasarathy from George Mason University. And we are thrilled to introduce you to PINNLab, a dashboard we've developed to teach parameter estimation for differential equation using a state-of-the-art technique called physics-informed neural networks implemented in MATLAB. Now, before we begin, I'd like to briefly thank the Aspiring Scientist Summer Internship Program, as well as the Department of Mathematical Sciences at George Mason University for their continued support in conducting this research. Our work is fundamentally motivated by the United Nations Sustainable Development Goals, specifically number 4 on quality education. Specifically, Target 4.3 emphasizes equal access to technical education. Currently, advanced mathematical modeling, like methods for machine learning and parameter estimation and even teaching differential equations, are locked behind high-level coding barriers. We set out to build a no-code dashboard that democratizes this access, allowing students to engage with complex modeling both visually and intuitively, following the framework you see on screen, where we start with a physical system and understand that using a mathematical model to engage students. Then we develop an analytical solution and a numerical solution, and finally we ground all of that truth in experimental data to really get students going into the mathematical modeling process. The core mathematical challenge we address is parameter estimation, finding hidden variables that go into the differential equations from real-world data. Traditionally, we use methods like least squares, but these methods require a guess-and-check forward-inverse loop that is computationally expensive and highly sensitive to noise in the data. Our solution is to use a state-of-the-art technique called physics-informed neural networks, or PINs. PINs don't need a traditional solver. They embed the differential equation directly into the neural network's loss function, handling complex inverse problems efficiently. We embed this technology within the standard mathematical modeling cycle. Instead of just stopping at an analytical solution, our dashboard PINNLab allows students to seamlessly validate and compare their models against experimental data, closing the loop of the scientific method. They can simulate using real-world scenarios and use our dashboard to predict the future outcomes once they've estimated those parameters, offering an all-in-one approach through a dashboard. Now we move into the educational framework. How are we actually using our dashboard to teach students? Well, to make this accessible, we've built a scaffolded curriculum of 9 units. It walks students step by step from basic one-dimensional population growth all the way up to complex multivariable fluid dynamics. The interface stays exactly the same, but the math grows with the student. Pedagogically, this follows the 5E instructional framework for teachers to guide students one by one through the process of differential equations. This starts by engaging the student with an interesting problem, allowing them to explore, then giving them a higher degree of independence as they explain the problem on their own, elaborate, and finally, evaluate. This form of evaluation is typically testing, but by doing this in an interactive dashboard manner, the evaluation can just be using PINNLab as a tool for students to conduct their own research of a problem that they are interested in applicable to the real world. Let me show you how PINNLab guides a student through these stages. First, we engage the student with the first module in our scaffolded curriculum, a basic exponential growth with the formula dy dt equal to ky. On the dashboard, students can configure the noise level and decide the true parameter k that they want our neural network to find. Once they hit start, they can watch the AI learn in real time, where they're the ones actually adjusting the parameters and seeing how their actions are shaping the neural network. The black dots are the noisy data generated forward using synthetic data simulation by the physics-informed neural network. The student can change the noise on that data, and then the physics-informed neural network, or the PIN, applies its fit and creates this blue line that cuts through the noise to find the actual growth curve, and using that, reverse engineer the growth rate k. Now, how does it do this anyway? Well, a standard neural network only minimizes the data loss. It's trying to connect the dots that it's given. But a physics-informed neural network, shown here on the right, also minimizes the physics loss. Using automatic differentiation, it calculates its own derivative and checks if it obeys the law dy dt equal to ky for this specific problem. It forces its guess to respect the laws of physics, and in doing so, it solves what's called the inverse problem. Given data, can we predict the parameters of the differential equation that was used to generate that data? Now, the limitation of this is that it forces us to need to know what the differential equation was beforehand. However, this is truly versatile because given a real-world problem with the dataset, a student can simply come in and upload the dataset, suggest an equation they think was used to generate that data, and then recover the parameters with an error percentage using PINNLab. Next is explore, where students can learn about first-order linear ODEs, or ordinary differential equations. The teacher can show them the traditional analytic method, that is, the method of integrating factor. This highlights a limitation. Analytic methods require a perfect equation. If you only have messy data, you need computational tools like a physics-informed neural network. Now, as you can see in this run, the student was able to set their own function q of t, as well as their own parameter k, which means they were involved in actually changing the equation. This gives them a powerful resource to understand how different equations operate under a physics-informed neural network that they are setting. Without any code, they can go in, change the number of epochs, and change the equation and see real-world results. Now, the explain phase. We introduce systems of equations with predator-prey dynamics following the Lotka-Volterra equations. There is no exact analytical solution here. PINNLab seamlessly handles the coupled system, finding 4 distinct parameters simultaneously while graphing the phase dynamics. One of the keys here is that PINNLab is not evaluated based on how accurate the neural network is, because the student is using the neural network and adjusting it on their own in real time, which means the student can go in and play with the parameters to see how different numbers of epochs yield the best results. We elaborate by applying this to epidemiology. Using the SIR model, a disease dynamics model originally developed by Kermack and McKendrick, students can input noisy infection data and watch the PIN accurately extract the infection rate and recovery rate. It shows the real-world power of the math they are learning, offering opportunities for teachers to interrupt students, teach a specific amount of content with the differential equations behind it, and then give the students an opportunity to use the content they've learned in a real-world manner. Finally, we reach evaluate. We want students to realize that the exact same tool they used for the basic ODE originally can be used for cutting-edge multivariable calculus and research with partial differential equations, or PDEs. We scale up to the next modules of our scaffolded curriculum. We introduce the heat and wave equations, moving from time-only ODEs to spatiotemporal PDEs in fundamental ones at that. The network is now learning a surface, estimating thermal diffusivity and wave speed all at once. Here you can see the output of a test run using PINNLab for those heat and wave equations. Now these are especially valuable because as we reach that next level of multivariable calculus, the students in a differential equations class, for example, will now be moving up to the next level and have the tools needed to conduct real-world multivariable calculus research. And the increased complexity of that research involves an even greater need for new, novel parameter estimation techniques such as PINs. Now the next module is what takes students into the world of research with the variable coefficient heat equation. Using PINNLab, we can capture a predicted value for a vector quantity, that is the notoriously difficult alpha diffusion coefficient as a function of x, meaning as it changes over space. To address this, we develop a finite difference solver in the background, using a Crank-Nicholson method. This allows us to simulate systems where the physical properties, such as diffusion, change across space, as well as teaching students about such finite difference methods. Teachers can guide them through explicit, implicit, and semi-implicit methods, and teach them how to discretize the entire system. Here you can see a run where the student inputs this complicated function alpha of x into the network, as well as sets their own number of epochs and noise level. Yet the network is able to seamlessly determine the value of alpha of x as a vector quantity that goes into this equation, despite how notoriously difficult the concept is. You can see it accurately captures the curves even though it gets closer and closer throughout the series of epochs. On the top, you can see how the predicted alpha of x is converging towards the real result. And on the bottom, you can see a snapshot of the temperature profile at time step 0.5. This brings us to coupled fluid dynamics, where contaminant concentration actively changes fluid velocity. Although this is a one-dimensional approximation, it offers the perfect opportunity for educators to explain coupled differential equations using this two-differential equation system, which couples a modified Burger's equation with an advection-diffusion equation to examine how a contaminant is spreading through a water system. Module 8 shows this basic equation, while Module 9 shows the same thing with two adjustments: alpha as a function of x once again, as well as the viscosity as a function of the concentration of the contaminant. This effectively shows how the contaminant's presence in the water affects the flow of the water, and how the flow of the water advects that contaminant and causes it to spread. As you can see in the top graph, the PIN isn't just estimating a single number anymore. It's successfully estimating an entirely unknown function. This has powerful applications for the real world, as with a real data set, unlike the synthetic data generated by the physics-informed neural network beforehand, a student would be able to capture real-world trends that could affect legislators and the people who run our societies. This leads us to a primary research application with multivariable calculus, water contamination. We use PINNLab to understand the effect of waterborne pathogens on real populations, looking at how they spread using a system of equations built upon the previous coupled system you saw earlier. This has applications in groundwater pollution, industrial discharge, as well as the spread of diseases. Specifically, this targets United Nations Sustainable Development Goal 6.1 on safe and affordable drinking water. As you can see in this graph from Statista, 1 in 4 people around the world still lacks access to safe drinking water, which is why we tried to figure out, can the system we've used for education be used as a research tool to allow students to draw conclusions without needing to know any code in MATLAB whatsoever? And the results were shocking. Specifically, we expanded our model to 2 dimensions using a 5 partial differential equation system, which obviously is significantly more complicated than the 1D approximations earlier. However, since we were drilling down on this one application, we figured we should probably go with more in depth, which is why we developed 5 partial differential equations, the first one for the velocity field and the second one for pathogen concentration, similar to the advection-diffusion and the Burger's equations from previous. Then we coupled that with an SIR system similar to module number 4. However, the partial differential equation version of that involves a susceptible population with recruitment, diffusion, natural death, and controlled transmission out of each compartment, as well as the infected population and their covered population, which effectively allows us to see how humans are interacting with both the water and with one another, and how that is causing the waterborne pathogen to spread. Using this 2D model, we got ground truths for the concentration, the water spread, specifically the fluid velocity, and the disease spread. By using this as a tool for research, we've achieved capabilities beyond that of a student without a coding barrier. Now, we even take that a step further by applying a problem of optimal control outside PINNLab, and we get real-world implications from filtration. Effectively, this is telling us where is the optimal place to put a filter in. It uses the physics-informed neural network in its original purpose for parameter estimation for all of the unknown variables, which, as you can see from the 5-system equation, there are quite a lot of unknown variables. And then using optimal control, it tells us what is the best place to apply a filter and how severe of a water filter do we need to apply to have the most positive results at the lowest cost. This really exemplifies the power of PINNLab. Without needing to know any code, the student is able to draw all of these possible conclusions just by knowing the mathematics behind the differential equation, being able to play around with the values of the epochs and the noise, uploading their own data set. However, uploading their own data set is a capability that is entirely optional for a student. They have the opportunity to simply look for the synthetic data provided for them. And by doing this, the student is able to really hit that last phase of the 5E framework on evaluation by conducting their own research. There is quite a lot of future work to be done. The most important part of that is making PINNLab a publicly accessible tool. The goal of this is to make MATLAB intuitive to all who can use it. So to make it available, we've explored options such as hosting on a public server, as well as working with MATLAB directly. In addition, we hope to let students expand their models, such as within the 4th module on SIR. Perhaps the students could add an extra compartment for exposed and change that to SEIR. We're also looking at implementing machine learning within our dashboard and having the opportunity for users to input all sorts of data set, with the difficulty with that being we don't know the different columns and the different parameters that go into that data set. But once we achieve all of that, PINNLab will truly be a tool for success for both students and educators in the realm of mathematics. We are leveraging the computational power of MATLAB and the novelty of physics-informed neural networks to teach students to use differential equations in a way intuitive and engaging to them. Thank you so much for listening to this presentation. If you have any questions or are interested in the software whatsoever, please don't hesitate to reach out at the email shown here. Thank you all and have an excellent day.